Welcome to lecture 3. In the last lecture we discussed how soils are formed, what is the origin of soils from parent rocks, which could be igneous, sedimentary, metamorphic. Then there are different processes, physical, mechanical, chemical, biological, different transportation agencies like water, wind, glaciers, rivers, what have you, all of these, and gravity of course. And sometimes you find soil formed in its own original location. We call them as residual soils. Once the soil is formed, how do I characterize? Towards the end of my last lecture, I was telling you that soil is what we call a three-phase material. What do I mean? For example, if I look at iron, steel, aluminum, etc., they're all single material. You only have a solid. Basically, I can even add some timber, wood, etc., but I would rather restrict. Even concrete, once it is formed, is predominantly solid. There may be few void spaces, but it's predominant. If I look at water again, it's a single material, just a fluid. If you look at a typical sponge in the house, you will find lots of air gaps inside or voids. So soil is something like a sponge, except that the particles are not bonded together. You will see, if I want to sketch a soil, you will have grains, particles, they are touching each other. They can be of different sizes, and you will have the spaces in between are called voids. The voids may be filled with water or they may have air. So you will end up in a typical soil. Three phases means a solid phase, a liquid phase, and a gaseous phase. And let us restrict ourselves to air, because in some petroleum refineries, etc., you may not have air, but you will have some other petroleum product. So liquid generally has water, except if you are working in a marine or coastal project, you may have seawater. So what you find is a typical soil consists of a solid material. These are all grains. They can be predominantly silica, or it can be feldspar, mica, or you can have a silt or a clay particle. So a soil consists of these three phases. In order to treat it as a material, I need to know how much is the solid part, how much is the liquid, and if there is air, how much is the air. So let us try to do a bit of arithmetic in what we call as weight-volume relationships. Unlike other materials, if I give you a piece of steel, metal, you know easily what is the volume and the weight, and you can find out either the density in terms of mass units or unit weight in terms of force units. Suppose I give you a lump of soil. Let us say it is 1 cubic meter. Can I imagine you have taken away all the soil particles and said the grains are put in here. The total volume is V. So I say, if I can find out the volume of all the solids, volume of the solids is here. The remaining part I'll say is volume of voids, which is nothing but the spaces between grains. But I can divide this into volume of water and volume of air. So please remember, we have taken a unit volume of soil, which consists of three phases: the solid phase, the liquid phase, and the gaseous phase, I'll call it. I can say the total volume consists of volume of solids, volume of water, and volume of air. Similarly, can I say the total weight is W. It consists of weight of the solids and weight of water. Volume and weight. I would like to define some terms so that we can describe this three-phase material. Should I consider the weight of the air? You will say the weight of the air is so negligible compared to the weight here, so we can neglect it. So can I say that the total volume of the soil is equal to volume of solids, volume of water, plus volume of air? I can also write it as volume of solids plus volume of voids, because volume of voids consists of volume of water plus volume of air. Similarly, can I say the total weight consists of weight of solids plus weight of water? Please remember, this is a very simple concept, but essential for you to appreciate, because the whole of soil mechanics we try to describe in terms of the relative proportions of these components. solids. Please remember that. So when we talk of different constituents and proportions, we need these parameters. Once again, I had taken a piece of or lump of soil. I put all the solid grains together and I found out the volume of the solids is called Vs. I had taken the water in all the voids and then called that volume of water. Whatever is remaining from the total volume, we call it as volume of air. The same I take the weights. If I take the total weight, I divide that into weight of solids and weight of water. Now let us define the different terms. First we define what is called as porosity. We use the symbol N, which is nothing but volume of voids by the total volume, and usually we express as a percent. What have you done? You have taken the volume of voids here and divided by the total volume. It will tell you how porous is the material. Basically, this can be 10%, 20%, 30, 40, etc. and you get porosity. What is porosity? Volume of the voids in the soil divided by the total volume. This was a good measure, but then we found that this volume is not constant. It can change due to temperature, the amount of water, whatever it is. As I said, some of the soils shrink in summer, swell in rainy season, which means this is not a constant. We found out another term called void ratio is a better description because it is defined with respect to the solid volume. Void ratio, we use the symbol E, and please remember it's a ratio and not a percentage. What we do is volume of voids by volume of solids. You can see that volume of solids is not going to change. The solids are not going to change in volume, they are always constant. It is the amount of water. In a dry season, the water may evaporate, and then because of that, there may be change in volume, but the solids will always remain same. You may say there may be slight thermal expansion, but we are not interested in that. Now, can you find a relation between porosity N and the void ratio? Just let us see. N is equal to volume of voids by total volume. Then I write the denominator as volume of solids plus volume of voids. And now you divide both the numerator and denominator with volume of solids. So if I do that, I have divided numerator and denominator with Vs, which is the volume of solids. I get Vv by Vs divided by Vs by Vs is 1 plus Vv by Vs. Can we write it as, by definition, Vv by Vs is equal to E, void ratio. So it becomes E by 1 plus E. So it's a very simple interrelationship between the two. If you know void ratio, you can calculate porosity, or if you know porosity, you can find out the void ratio. So let me write this for you to remember. N is equal to E by 1 plus. Can you solve this by cross multiplication? I want you to derive that it's N is equal, E is equal to 1 minus N. So these are related. Another way you have to describe is, you have the void space and you want to say, is this soil fully saturated or not saturated? Which means if Va is 0, total volume of voids is equal to volume of the water. When there is no water, it's equal to volume of the air alone. So we describe another term called degree of saturation. We use a symbol S, also expressed as a percentage to 100. You can see that if volume of water is equal to volume of voids, this ratio is 1, multiply this, you get what you call as 100% degree of saturation, and this is called a saturated soil. And if volume of water is 0, then you will get 0% if VW is 0. It's a completely dry soil. So degree of saturation can vary from 0 to 100%. Why is it important? For example, I have ground level here, and if I dig a pit, I find the groundwater level here. If I take a sample below the groundwater level, you just say go to a nearby well, you will see where the water level is in the well, and so any outside the well also the water level will be the same. And if I look at the soil sample here, this sample is below the groundwater level. the top phreatic surface. So is there any possibility of air being there? The water is replacing air in every void, so you will get a saturated soil. Whereas from here, as you go towards the surface, chances are the water gets evaporated, so the degree of saturation may decrease from 100 near the groundwater level. By the time you go to the surface, you may get very, very small. You may sometimes call it as hygroscopic. It could be maybe 4-5% degree of saturation. So in the same soil, you find the amount of water can vary depending on the depth and the location of the groundwater level. That is why we need to define the degree of saturation. Let's now pass on to the relationships between weights. We talked about the relationships between volumes. Now we say the weight relationships. So we have what's called as water content, or sometimes we use the word, or these are interchangeably used, moisture content, and we use the symbol W is equal to weight of water divided by weight of solids. Again, we express as a percent. So what I'm trying to find is the ratio between the weight of water within the unit volume we are looking at, and take it as a ratio of weight of solids. And don't think this can be something less. There are some soils where the water content can be greater than even 100%. That means the amount of water within the voids can be very, very high. We'll find out why it is so later. But basically, this can vary from very low value of even 0 to maybe something like 200%. So please remember, we are looking at the relative weight of water with respect to weight of solids, and we will get either water content or moisture content. In some textbooks, it's referred as moisture content, and in many, it's written as water content. It's a very important parameter. It's easy to measure this. All that I do is I take a soil sample from the field. I take a small container, one of those small cup-like thing. I take the weight of the cup. Let's say I call it as W0. I put a small lump of soil. All I need is a good balance, which is accurate up to, let's say, 0.1 or 0.01 grams. So then I have weight of cup plus the moist soil. I call that as W1. You can use any of these simple balances, or nowadays most labs have this what you call electronic balances with a pan. Just put it on top, press a button, you get the reading. Then after I take this reading, I put this cup with the soil in an oven and heat the cup with soil sample to at least 105 degrees centigrade for 24 hours. What happens when you are heating for more than 100 degrees for sufficiently long time? Would you agree that all the water will get evaporated? So what do you get now? You will only have, when I take this cup and the soil out, cool it and take a weight, then I'll have weight of cup plus dry soil. Let's say I call it as W2. The weight in grams, whatever you determine. So I'll have weight of empty cup, weight of cup with moist soil, and weight of cup with dry soil. Please remember, as I said, usually we expect the temperature in the oven to be 105 degrees. And it has to be heated to 24 degrees. This is the standard oven. Nowadays, in some laboratories, they are replacing the oven with a microwave, and you can heat it for about 10-20 minutes, and then you will expect all the water to get evaporated. Once you do that, what will be the weight, difference of weight between W2 minus W0? What is the weight? W0 is the weight of the cup. Weight of the cup and dry soil is, so can I say weight of soil, weight of dry soil is equal to W2 minus W0, whereas weight of wet soil is equal to W1 minus W0. What will be the weight of water? If I take the difference of W1, weight of moist soil, and cup, and subtract the weight of cup and dry soil, will I not get the weight of water? Please remember, what is W1? Weight of cup with moist soil, and W2 is cup and dry soil. So this will give me weight of water is W1 minus W2. So you can easily determine the water content is equal to W1 minus W2 divided by W2 minus W into 100. you get the water content. Very easy to do, and this you should be able to do in any laboratory. Then after this, we'll pass on to the estimation of unit weights or densities. Here I would like you to revise your concept. In physics, you would have studied about density. I'll call it as a mass per unit volume, whereas we call it unit weight, which is force units by unit volume. In engineering, we use this. So here I can talk in terms of grams per cc, for example. Here I have to say kilonewtons per cc or kilonewtons per meter cube, etc. Because we are now talking of a large volume and we are talking of the force, gravity force acting. So you know that force is equal to mass into g, and g you know is nothing but 9.81. As long as you are very clear about the units, you can interchange the two. This would be force units are in SI, kilonewtons per meter cube, for example, whereas mass is in grams per cc or meter cube, whatever it is. And I'm multiplying by the unit weight of water that will give me, or I mean, acceleration due to gravity, which is 9.81. And please remember, the density of water is 9.81. We normally take it as, 1000 or 1 ton per meter cube, and this will be equal to 9.81 or 9 kilonewtons. So please remember that we start with water, and am I right? 9.81, 1000 grams, so 1 kg. Now come back to the soil here. I would like to define now. We are now talking of this soil here. So can I say total or bulk unit weight? Use symbol gamma B or gamma total is equal to W by V. The weight, total weight divided by total volume gives me unit weight of the sample. We express usually in kilonewtons per meter cube. So this can be anywhere from, let's say, 14 to 20 kilonewtons per meter cube. What we have found out was total weight divided by total volume. Suppose I want dry unit weight. We call it as gamma dry. I take it as weight of solids by the total volume. Please remember, I'm not looking at the weight of water, so I have removed that and say I'm only considering weight of solids. So I'm looking at what is happening here. Weight of solids by weight of volume. Again, this is in kilonewtons per meter cube. So these are the two. Suppose, again, like we talked earlier, ground level is here, groundwater level is here. I would like to find out what is the effective weight of a soil below the water table. If I use the Archimedes principle, because at certain depth you have the buoyancy, you will get gamma submerged, which is called the submerged buoyant unit weight, which will be equal to gamma total minus gamma W. You know that Archimedes principle says the effect of buoyancy is equal to the weight of water it displaces, and the weight of water it displaces is equal to volume into unit weight of water. So we find out the submerged unit weight. We also define one more term called the saturated unit weight. When VA is equal to 0, then this V is nothing but the total volume is sum of, because this is volume of air is 0, we will have volume of solids plus volume of water is equal to total volume. There are several interrelationships again between these different weights. Let's see how we can combine them or show what is the relationship. For example, we have gamma total is weight of total weight by volume. Can I say this is weight of solids plus weight of water divided by volume? Can I take it as weight of solids plus, I have expressed this as a ratio and I take in common factor. So can I write it as weight of solids by total volume into 1 plus weight of water by weight of solids? Can I say it is nothing but water content? So now I have a relation between gamma dry into 1 plus W gives me the total unit weight. Or if I want gamma dry is equal to gamma total divided by 1 plus W. Like this you can do a lot of manipulations around and find out what are the various values. Again, let's gamma dry. Can I write it as, before this I should define also specific gravity G, and we actually should say GS for solids. Can I say it's equal to rho solids by rho water, or can I say gamma solid in terms of unit weight gamma water? Specific gravity is defined with respect to the density of water. So what you will find here is that G is expressed in terms of density or in terms of unit weights, and G is the specific gravity. You can write GS, but since we are only dealing with one material, that is solids, in some books you will not find the subscript S. You can use or you may not use GS. It is the same. When I say GS or G, I am talking of specific gravity of the solid component of soil. Now, can I say weight of solids by volume of solids is nothing but gamma solid, which is equal to specific gravity into gamma W. Please remember, I can write it as gamma solid by 1 plus C, or I can write it as G times gamma W by 1 plus C. So now we have a relationship between dry density and void ratio through specific gravity and the unit weight of water. As I said, unit weight of water is known. It's a standard universal parameter. Weight of 1 cc of water is 1 gram. So you can say 1 gram per cc. Everybody knows gamma W. So if I know specific gravity, I can get gamma, specific gravity, unit weight of soil solids. Here I would like to say that fortunately for us, G is also not a major variable. For sands, which consists of silica, G is 2.65. No matter where you get the sand, you can get it from any coastal area, from India, USA, abroad, anywhere you find that silica. Then what we have very high clay minerals, very fine particles, they vary from G 2.67 to maybe 2.75. It's a very small range and they won't make a big difference. You may find it can be 2.69 to 2.73. Doesn't make a big difference in terms of calculations. You may find it or you may not find, and take it from a textbook and use the value. You will not make any major mistake. The third material nowadays we are using is called fly ash. Now this is a product from all our thermal projects, whether it's Ramagundam, Visakhapatnam, Vijayawada, Kinnarsani, etc., where we burn coal to generate power. When you burn coal, whatever is remaining is called the ash, because it's a very fine particle. It flies, so it's called fly ash. We are using fly ash as a construction material, as a replacement for soil, and its specific gravity is lighter, around 1.9 to 2.1. So you find that these are the three kinds of material. If you end up using organic material, luckily we don't have in major part of our peninsular India. We have found some in North Assam, near Himalayas, and in Arunachal Pradesh. There, of course, again, they are very light materials. So specific gravity can be less, and that depends on the amount of organic matter that you have. So what you have found out now is that the relationships between solid, volume component and the weight component, and in terms of density. So using this, you can do a lot of calculations. I would like you to refer to the book and try as many examples as possible.